Alright, this is a video of our test on advanced polynomials. We're going to factor, we're going to find zeros, look at graphs, all that good stuff. But let's start with factoring. So problem number 1. Hopefully you recognize this as the sum of two cubes. And we learned that the sum of two cubes will always factor as a binomial and a trinomial. The binomial is just going to be the cube root of each of these things. So the cube root of 64 is 4, right? Because that's 4 to the third power. Of course, x will give you x to the third power. It's plus, so I'm just going to bring that down. And the cube root of 27 is 3. So there's the binomial, 4x plus 3. Now, the trinomial I'm going to get from the binomial. So I really could forget about this and just now focus on the binomial. A trinomial has, 3 parts. Alright? I'm going to do the first and the third part right now. And it comes from squaring these two things. If I take 4x and square it, I'm going to get 16x squared. If I take 3 and square it, I'm going to get 9, positive 9. Alright, so that's how you find the beginning and end of the trinomial. The middle comes from multiplying these two things together. It's always going to be the opposite sign, so if this is positive, this will be negative. But 4x times 3 is 12x. Okay, maybe I'll just put a little side note here that we're doing 4x times 3. So that's how you get the middle. And that's it. We have factored it. Alright, let's look at problem number 2. Now I'm noticing that there are 4 terms, and our best bet for factoring when there are 4 terms is grouping. So let's look at these first 2 terms as a group and the second 2. GCF. Let's see. Well, both of these are divisible by 16, so I'm going to do a 16. And then I see x to the third and x squared, so they both have at least x squared, so let's go ahead and pull that out. So there's our GCF. Okay, that is going to leave behind x plus 2. 16 times 2 is 32. Now, here, this minus x minus 2, it's easiest if we sort of put a 1 here and think of it as factoring out a minus 1. Alright, as we build our parentheses, we will have x plus 2 again. Now think about it, it makes sense. Look at this negative 1. Negative 1 times x would be negative 1x. Negative 1 times positive 2 will give you negative 2. So it does make sense. Now this x plus 2 itself is a common factor. So we could bring it out front, and we will have x plus 2 times the blue stuff, 16x squared minus 1. Now, be careful not to stop here. Can you see why I can keep going with this? I'm going to need a little bit more space. The 16x squared minus 1, that can be factored further as the difference of two squares. Alright, so this can factor as 4x plus 1 and 4x minus 1. Okay, and we'll just bring down the x plus 2, and that will be the final answer. Okay, so this is the final answer right here. Alright, Number 3 is the difference of two squares once again. We just have to be careful with it. X to the 4th power can factor as x squared times x squared. Obviously 81 is 9 times 9. So the pattern of the difference of two squares, we'll do 1 plus and 1 minus. So x squared plus 9 and x squared minus 9. Now, the x squared plus 9 is done. You cannot factor that further. But x squared minus 9 is the difference of two squares. So, I can bring down this x squared plus 9, but the x squared minus 9 I will factor further as x plus 3, x minus 3. And that will be the final answer. Okay. Now, looking at number 4, the first step of factoring is to look and see if there is a common factor. And we need to factor out the GCF. Now I see the 2, both of these are even, so it's definitely going to be divisible by 2. And I see the x and the x to the 3rd, so they both have at least one x. So this is the GCF. So that is going to leave behind, if I divide here, that's going to leave behind x squared plus 36. Okay, and if there's any doubt as to where I got this from, once you have the GCF, what you are really doing is you are dividing by that GCF to see what goes on the inside. So we've got this. Can this factor any further? No. That would be a no. Let me move this down a little bit. So yeah, this is the final answer. Okay, let us move on. Alright, so we're supposed to use this function to answer the questions below. List the possible rational zeros. This word possible is a keyword that reminds us to use the rational zero theorem. Alright, that's the one where we say, okay, possible zeros will be of the form numerator over denominator. Let me zoom in a little bit. Okay, numerator over denominator, where the possible numerators are going to come from the constant factor. See, the constant factor here is 2. So this 2 will give us the possible numerators. Now when I say that, I mean the factors of 2, which are just 1 and 2. Now the denominators are going to come from the other factor, the leading coefficient. And again, the factors of the leading coefficient are 1 and 2. So we are just going to mix and match these numerators and these denominators to come up with the possible rational zeros. So, starting with a denominator of 1, if I do 1 over 1 and 2 over 1, well, 1 over 1 is just 1. And 2 over 1 is just 2. So those are the first two possible rational zeros. But then we switch, and now we'll go ahead and look at 2 as the denominator. Okay, so now I'm using these numerators again. I've got 1 over 2. Alright, so that's going to be 1/2. And 2 over 2. But 2 over 2 is 1, and we already have that, so no new zeros there. So we've got these 3 possible rational zeros, but actually there are 6 because each of these could be positive or negative. So we'll just put a plus or minus here. So these are the 6 possible rational zeros. All right? That means any other zeros would have to be imaginary, or maybe there's a square root in there or something like that. But we'll find out exactly what they are. By the way, at a glance, we should know how many actual zeros there are. And of course, we know that by looking at the degree. So because this is a degree 3 polynomial, we know that there will be 3 zeros when the story is all told. Okay, we're supposed to write in factored form and find all the zeros. So we are just going to go ahead and start trying out these possible zeros one at a time until we find one that works. So here we go. Let's just start with positive 1. Alright, our first possible rational zero. And let's see, so our coefficients are 2, 1, negative 5, and 2. So here we go, 2, 1, negative 5, and 2. So let's see if this one works. Alright, when I say it works, I mean there should be a remainder of 0. Okay, so we'll bring this down. 2 times 1 is 2, and that makes 3. 3 times 1 is 3, and that makes negative 2. Negative 2 times 1 is negative 2, and that does, in fact, make 0. So we got lucky. First one we tried worked. Okay, so that means we found one actual zero. It is 1. So let's go ahead and put that on our list. Okay, so we have a 0 of 1, which corresponds to a factor of x minus 1. Yeah, I now see that we were supposed to put these possible zeros on the line, so let me do that. Plus or minus 1, plus or minus 2, and plus or minus 1/2. Okay, let's get back to work. Now, once we get down to a trinomial, we can go ahead and try to factor it, and if that doesn't work, we'll just use the quadratic formula. So this is going to be 2x squared plus 3x minus 2, putting those coefficients back in. Let's see if it factors. Alright, 2x squared can only be 2x times x. 2 can only be 1 times 2. Now it matters whether I put the 2 here or here, but I know it can't be here because that would cause a common factor, and that shouldn't happen. So it must be, if it factors at all, it's going to have to be 1 times 2 like that. Now let's check the inner and the outer, because that has to equal the middle of positive 3x. Okay, so inner we have 1x. Outer we have 4x. Now we can make a positive 3 out of that if the 4 is positive and the 1 is negative. So that means a negative 1 here and a positive here to make the 4. Does that make negative 2? Well, sure. Negative 1 times positive 2 is negative 2. So this is the correct factorization. 2x minus 1, x plus 2. Okay, so we'll have 2x minus 1 and x plus 2 to complete the factored form. Now, these factors will tell us the other zeros. So from this factor, we get a 0 of 1/2. And from this factor, we get a 0 of negative 2. Now, of course, what I'm actually doing when I list off these factors is I'm setting these equal to 0 and I'm solving. So just to be clear, in my mind I'm setting 2x minus 1 equal to 0, and I'm setting x plus 2 equal to 0. And I am mentally doing this. 2x equals 1. Okay, x equals negative 2. So right there, that's where the negative 2 came from. Meanwhile, divide both sides by 2. So I'm getting x equals 1/2. Okay, that's where the 1/2 came from. Okay, well, that's the end of this question. We had our possible rational zeros, and sure enough, our actual zeros turned out to be from among them. Okay, so that was number 5. Alright, number 6. This time we're given the graph to help us out. Okay, so we're going to use the function and the graph to answer these questions. We need to write this in factored form and find all of the zeros. Well, it looks like we can get 2 of the zeros right off the graph. So we have a 0 here and here. So that's negative 1 and positive 2 right off the graph. So let's go ahead and record that. So we have a 0 of negative 1 and positive 2. So from a 0 of negative 1, we can infer a factor of x plus 1. From the 0 of positive 2, we can infer a factor of x minus 2. Now look back at the function. Can you tell me how many zeros there will be total when we're done? Well, hopefully you were thinking 4. There will be 4 because that's the degree. So far we have 2 of our zeros and the factors that go with them. So we're looking for 2 more. Based on the fact that there are no other x-intercepts, you can bet they are going to be imaginary. Okay, well, let's use the 2 zeros we have and start doing our synthetic division. Alright, so we'll start with negative 1. Alright, so the coefficients are 1, negative 5, 7, 3, and negative 10. Alright, this one should definitely work because we saw the 0 right on the graph as an x-intercept. So this is going to come down. 1 times negative 1 is negative 1. This will make negative 6. Negative 6 times negative 1 is positive 6. That's going to be 13. 13 times negative 1 is negative 13. Together, this makes negative 10. And negative 10 times negative 1 is positive 10, which does, in fact, make 0. So, notice we're getting smaller. We started off with 5 terms, and now we're down to 4. But we really need to get down to 3 so we can either factor or use the quadratic formula. So I used the negative 1 and got it down to 4. But we have one more 0 that we can use. So let's go ahead and use the 2 to get it down to 3. So we will take that 2 and pick up right from here. Please do not go back to the original coefficients because we need to get even smaller. So we need to pick up right from here. So we will just put the 2 right here and just make a new line below. Okay. Alright, so 1 times 2 is 2. Together that makes negative 4. Negative 4 times 2 is negative 8. And together that's going to make 5. 5 times 2 is 10, which makes 0. Okay, and that brings us down to 3 terms, which is just what we need to either factor or use the quadratic formula. So putting the variables back in, this is x squared minus 4x plus 5. Okay, and we need to solve this equation. It's not going to factor. I know that because we already decided that the remaining zeros are going to be imaginary. So I know this isn't going to factor. It looks tempting though, so you might be wondering, well, wait a minute, why doesn't it factor? It kind of looks like it'll factor, so I better show you why it won't factor. 5. There's only one way to factor and get 5, and that's 1 times 5. And you're probably thinking, wait a minute, I can make negative 4 out of this, because inner we have 5x, and outer we have 1x. We can make that negative 4 that we want if we make the 5x negative and the 1x positive. So that would mean we'd have the negative here and a positive here. So why am I saying that it's unfactorable if I can get that middle just like this? Yeah, the problem is the positive 5. We're not getting a positive 5 out of this. Negative 5 times positive 1 would be negative 5. So close, but no, it actually does not factor. So that means we'll have to scrap that and go for the quadratic formula instead. So A is 1, and B is negative 4, and C is 5. So you remember the quadratic formula is like this. Opposite of B plus or minus the square root b squared minus 4ac all over 2a. There's the quadratic formula for you. So let's see what we've got. Opposite of b, well, that'll be positive 4 plus or minus square root all over 2a. Well, a is 1, so 2a will just be 2. Now, this discriminant, this b squared minus 4ac, I always like to calculate that separately. So b squared minus 4ac. b is negative 4, so b squared is 16. So 16 minus 4 times 1 times 5. Okay, in other words, 16 minus 20. So that's just going to be negative 4. Okay, so our discriminant here is negative 4. Now, notice this is one of those ones where we have negative under the radical. So that is going to be I, imaginary. So we will have 4 plus or minus I square root of 4 over 2. But square root of 4 is a perfect square, so that's just going to give us 4 plus or minus 2i. Square root of 4 is 2. So 4 plus or minus 2i over 2. Alright, now let's go ahead and reduce this using our heart, like this. Okay, it's got to be all or nothing. If all three of these numbers are divisible by something, then we must do it. And they are all divisible by 2. So that is going to give us, alright, so that'll be 2 plus or minus, this will be 1, but I don't really need to put the 1, so I'll just put I. And again, 2 divided by 2 is 1, and again, I don't need to show that. So it's just 2 plus or minus I. So these are the two remaining zeros. Okay, so as far as the zeros, we knew there would be 4. So we had -1 and +2, and now we're going to add 2 plus I and 2 minus I. Now, what about the remaining factor or factors that correspond to these zeros that we just found? Well, as soon as we had this trinomial that turned out to be unfactorable, this trinomial is the rest of the factored form. So we just need to copy this down. X squared minus 4x plus 5. So x squared minus 4x plus 5 will be the rest of the factored form. Okay, so that is it for problem number 6. Alright, number 7. So we're supposed to use this function and the graph to answer the questions below. Okay, so this is just like the last problem. Alright, well, this time it looks like I can see where all 4 of the zeros are, but one of them is some sort of a fraction. So I can't be sure. I mean, maybe it's 1/2, but I'm not going to gamble on that. Let's focus on the 3 that are more obvious. So I've got -3, -1, and +1. Okay, so let's write that down. So I've got -3, -1, and +1. And as far as factors, that translates into x plus 3 and x plus 1 and x minus 1. Okay, so looking at the polynomial again, the degree is 4. So we know there are 4 zeros, and you can see them all right there on the graph, but we just need to be sure what that last one is. So let's go ahead and use our synthetic division and find it. So I'm going to start with 1 just because that's an easy number to use. Okay, so the coefficients are, alright, we've got 2, 5, -5, another -5, and 3. Okay, 2 times 1 is 2, so that's 7. 7 times 1 is 7, so that's 2. 2 times 1 is 2, so that is -3. -3 times 1 is -3, so that is 0. So far, so good. So we use the 1. Let's go ahead and do the -1 now. So I'll just go ahead and put my -1 right here. Let's draw another line, keep on going. Alright, 2 times -1 is -2, so that is 5. 5 times -1 is -5, so that is -3. -3 times -1 is +3, so that is 0. Okay, so I could factor this right now. I could even, because I've got yet another 0, I could keep going and use that to go further. But I'm going to go ahead and factor this because, you know what, factoring is fun. So I've got 2x squared plus 5x minus 3. So if I factor this, 2x squared will be 2x times x. 3 can only be 1 times 3. Now the 3 might go here, so if this doesn't work out, I'll try it the other way. Inner, I've got 1x. Outer, I've got 6x. I'm trying to make a positive 5x middle. I can get that if I have a negative 1 and a positive 6. So that would make this negative and this positive to make the 6. Will that make negative 3? Why, yes it will, because negative 1 times positive 3 is negative 3. So this is the correct factorization. So look back at our factors. Okay. See that x plus 3 that's right there? Alright, that's the x plus 3 that we just found. Alright, so we already had it. So this 2x minus 1 is the missing factor. So all we have to really do is add the 2x minus 1 to the list. Because remember, we knew we were only missing one more 0. So we're not going to add another x plus 3. We're just going to add the 2x minus 1. And that, of course, will give us our last 0 of 1/2. And again, I'm really getting that by doing 2x minus 1 equals 0, and I'm adding 1 to both sides. So that'll give me 2x equals 1. If I divide by 2, I get the x equals 1/2. Okay, so that is the end of this problem. We have our factored form, and we have all 4 of our zeros. Now, I'm just going to go back and show you. I was mentioning that I could have kept going, so I feel like I should show you that. So another thing that we could have done, maybe I'll do it in gray. Back at this step, okay, where we had the 2 and the 5 and the negative 3. Okay, and we had used 2 of our zeros that we saw from the graph. We had used the 1 and the negative 1, but we hadn't used the negative 3 yet. So I just want to be clear when I say that we could have used it to keep going. This is what that would have looked like. If I used the negative 3, I could have gone one more level like this. Alright, 2 times negative 3 is negative 6, so that's negative 1. Negative 1 times negative 3 is positive 3, so that's 0. If I put the variables back in, then this would be 2x minus 1. So you see this 2x minus 1 is the same factor that we were missing, that last factor of 2x minus 1. So we could have done it that way by using the negative 3, and that would have saved us from having to factor. So if you're really bad at factoring, then you would really prefer to use all of your zeros until you run out. But if you're great at factoring like I am, then it's more fun to just factor. Okay, well that really is the end of number 7. Alright, for number 8, we're supposed to write a polynomial function for the graph shown. Consider zeros and end behavior and leave your answer in factored form. Okay. It's mostly all about the zeros. So here I see we have a 0 at negative 3. So I know I'm going to have a factor. Let's see, f of x equals. I know we're going to have a factor of x plus 3 from that. Now looking at the behavior here, see how it's a bounce? We learned that whenever there's a bounce at the 0, that means it is multiplicity 2. It's a double root. Okay, I keep looking over here and I see that we have a 0 at 4, positive 4. That means we're looking at a factor of x minus 4. And since it goes straight through, that means that is a single factor and a single root. And then finally, I see that we have another 0 here at 8. And this is what we call an inflection. See how it's sort of flattening out, but then it goes on through. That is an inflection. And we learned, well, first of all, we have positive 8, so that means we're looking at a factor of x minus 8. But an inflection corresponds to a triple root and a triple factor. So the polynomial is basically going to look like this. Now we just have to worry about should there be a minus sign here in the front. Well, see how both ends are pointing up? That would be just like a positive parabola, alright? That would be the same end behavior as a positive even polynomial. So we'll leave it positive, and we're noticing that this must be an even degree polynomial. So let's just double check with what we have. I see we have 2 of these, 1 of these, so that's 3 so far, and then 3 of these, so that's 6. So we do have an even degree, so it kind of matches what we're thinking, and so we'll just leave it positive and be done with it. So that is number 8. Now over here we've got number 9. This is sort of the opposite. So this time we're given the polynomial and we're supposed to sketch a graph of it. Now let's start with these zeros. With a factor of x minus 1, that means we have a 0 of x equals 1. With a factor of x plus 3, that means we have a 0 at x equals negative 3. Okay, so 1 and negative 3. So we're going to have a 0 here and a 0 here. Okay, now notice this is a double, so there should be a bounce happening here. This is a triple, so there should be an inflection happening here. Now, let's take a look at the degree. I've got 2 of these, 3 of these. So that means the degree is 5. Okay, so the important thing about the degree being 5 is that it's odd. And now I see that it's negative. Okay, so it's whenever there's odd degree, it's going to have the end behavior like a cubic. Alright, a cubic graph typically looks like this. Reminds me of a capital N, but this is the positive version, like a right side up N. The negative version would be like an upside down N, like this. Okay, this would be the negative version. And all odd functions have the same end behavior, just like a cubic that we memorized. But since there's this negative sign in front, then it's the negative version that we are going to model. So our graph should have this type of end behavior. So that means it's going to start off high on the left and end up low on the right. So if we start off high, like start off over here somewhere, as we come in, okay, remember at the negative 3 we should have an inflection. So there should be an inflection here, and then there should be a bounce here. So let's try to start off high and just make that happen. So an inflection is when it sort of comes in like it's trying to be a parabola. But then it switches and it still is a parabola, but it's going in the opposite direction. Now we've got to curve around, giving ourselves enough time to bounce at 1 here. Alright, so it's got to bounce right here. Okay, and it's got to bounce off and keep going the way that it was going. Alright, so the graph is going to be something very much like this. Okay. And so it has the right end behavior. I've got an inflection here and a bounce here, so we are good. So that's it for number 9. Alright, number 10. Alright, we've got this function. They're asking us straight out, how many roots or zeros will this function have? Well, we see the degree is 4, so we know there will be 4. So, okay, that was easy. Now we're supposed to use the table to find all the roots of the function. Now, if we see any zeros on the y side, we know that those will be, on the x values, are zeros of the function. So we should be staring at this 2 and this 7. So those are 2 zeros that are basically given to us from the table, 2 and 7. So let's go ahead and record those. Alright, so we had 2, and that will correspond to a factor of x minus 2. And then we had 7, which will correspond to a factor of x minus 7. So we know there will be 4 zeros, so we've got 2 of them so far. So let's use our synthetic division to find the rest. So I'm going to need those coefficients. Alright, so I'm going to start with the 2 because that's a pretty easy number to use. So the coefficients are 1, -9, 23, -81, and 126. Alright, 1 times 2 is 2, so that is going to be -7. -7 times 2 is -14. Alright, if you put this together, you're going to get 9, and then 9 times 2 is 18. So that's going to make -63. -63 times 2 is -126, which makes 0. Alright, so we used one of our zeros. We still have one left. Alright, so we used the 2. Now it's time to use the 7. So we'll just go ahead and put 7 right here. One times 7 is 7. That makes 0. Times 7 is 0. That makes 9. 9 times 7 is 63. And that makes 0. So, well, this would be a trinomial, except for the middle is 0. So, putting the variables back in, what we have is x squared plus 9. This cannot be factored, so that means this is the remaining factor of our factored form. So let's go ahead and add that to the list. So we've got x squared plus 9 is our remaining factor. If we go ahead and set that equal to 0 and solve, so we have x squared plus 9 equals 0. Subtract 9 from both sides. Alright, so that gives us x squared equals -9. This is one of those ones where we take the square root of both sides. Alright, don't forget that the solution will be plus or minus. So that's going to be x equals plus or minus. Now we know we're going to have I because of the negative under the radical. So for ignoring the negative for a minute, the square root of 9 is 3. So because of the negative under the radical, that is 3i. So plus or minus 3i. And I'd like to write it separately, so let's go ahead and put 3i and then negative 3i. Okay, so those are all the zeros, and this is the factored form. Alright, number 11. Students were asked to find all of the roots of this polynomial. Patricia claims that the only two roots are negative 1 and 2. Is she correct? We're supposed to explain. Well, obviously she's not correct, because the degree is 4. That means that there are 4 zeros. And this is only 2 of them. So, yeah, there must be 2 more. So just write that up in some sort of sentence, and then that's it. Okay, something like this would be good. Okay, because the degree is 4, we know there are 4 zeros. Therefore, negative 1 and 2 cannot be the only zeros. Yes, kids, it's just that easy. Alright, number 12. Write a polynomial function f of least degree that has the leading coefficient of 1 and it has these zeros. Okay, well, it all starts with these zeros. First of all, remember that imaginary zeros always occur in plus-minus pairs called conjugates. So the fact that there's a 3i here means that there's also a negative 3i automatically included. So it looked like they were giving us 3 zeros, but really they're giving us 4. Now let's turn each of these zeros into a factor, and we're going to have to multiply them all out to get the answer. So having a 0 of negative 4 translates into a factor of x plus 4. Having a 0 of 0, you could think of this as a factor of x minus 0, but that's kind of silly to have a minus 0 there. It's x. Let's just be honest with ourselves. So we have 2 factors so far, x plus 4 and x. Now these guys, the imaginary ones, we'll just set it up the same way. So 3i will correspond to a factor of x minus 3i. And negative 3i will correspond to a factor of x plus 3i. So if we multiply all this together, we will come up with a polynomial in standard form. So looking at the blue side of this polynomial, it would be very easy just to do the distributive property here. So that is going to just give me x squared plus 4x. Okay, that was easy enough. Now, looking at this side, it's going to take a little bit more work, but still not too bad. So we will have to do the distributive property twice. So if I distribute the x, that is going to give me x squared plus 3ix. Okay. Now, if I distribute the negative 3i, I'm going to get negative 3ix. Negative 3 times positive 3, so I'm going to have negative 9i squared. Okay, because I times I is I squared. Now, please remember that I squared is equal to negative 1. Alright, now what's going to happen is these are going to cancel each other out because we have a positive and a negative. They're gone. So that means I have x squared. I'm just bringing that down. Now this minus 9 is going to become plus 9, because this is really, we've got negative 9i squared, but I squared is negative 1, so that's negative 9 times negative 1. So that is positive 9. So that's where this came from. So putting it all back together. So I have x squared plus 9, and I have my x squared plus 4x. Now we have to multiply all this together. So let's do that again. So if I distribute the x squared, okay, x squared times x squared is going to give me x to the 4th power. X squared times 9 is going to give me 9x squared. Now if I distribute the 4x, alright, that's going to give me 4x to the 3rd power. And then if I do 4x times 9, that is going to make 36x. Now these are not in the right order for standard form, so all I need to do now is rewrite this in the proper order. And let's go ahead and call it f of x. Okay, so in standard form we're going to have x to the 4th power, alright, plus 4x to the 3rd power, plus 9x squared, plus 36x. Okay, and there you go. That's number 12. Long division. Setting up this long division problem, you got to be careful which one of these goes under the division symbol. So we will actually put the x squared minus 3x plus 9 out front. Okay. And then under here goes the x to the 3rd power. Now notice how it skips directly from x to the 3rd power straight to the constant. We're going to need a couple of 0 terms, people, as placeholders. So I'm going to need a 0x squared and a 0x term to hold the spot. And then my plus 27. So this is how you set it up. And you should be asking yourself, x squared times what will make x to the 3rd power? Well, that's going to be x squared times x. Alright, x squared times x is going to make x to the 3rd power. Once you have this, you take it and you distribute it. So x times x squared, of course, is x to the 3rd power. That's why we picked it. But x times negative 3x is going to be negative 3x squared. And x times 9 is going to be 9x. Okay, now you immediately subtract by changing all the signs. So this is going to become minus, this will be plus, and this will be minus. So these are gone, but here I will have 3x squared. Bring that down. Together these will make minus 9x, and I'll bring down my plus 27. Then we sort of start over, and once again we ask ourselves, x squared times what will make 3x squared? Well, clearly all we need is that 3. So I'll put my 3 up there. Now I will take that 3 and I will distribute that 3. So 3 times x squared, of course, is 3x squared, just like we planned. 3 times negative 3x is going to be negative 9x. 3 times 9 is 27. Okay. So we will subtract by changing the signs. So minus, plus, and minus. In this particular case, everything winds up canceling out. So that means we have a 0 remainder. So really this x plus 3 is the final answer, is the quotient. So that's what we'll put here on the line here, x plus 3. And that's it for number 13. Okay, number 14. Determine algebraically whether the given function is even, odd, or neither. Algebraically. Well, what we have here is the original function. I'm just going to put a little box around that. Alright, for these problems we always need three things. We need the original function, which of course is f of x. But then we need the opposite function, which is negative f of x. Alright, and we will get that by multiplying this by -1, just distributing -1. Basically, just we're changing all the signs. So this will become negative 4x to the 5th power and positive 3x to the 9th power, positive 2x to the 3rd power, and negative x. Okay, I'm going to go ahead and put a box around that as well. Okay, so we've got the original function and the opposite function. The third thing we need is f of negative x. Alright, we will go ahead and label it. And that means we are taking the function and we're substituting negative x for all the x's. So we're going to have, let's see, right now everything that has an x I'm going to put a parentheses. So that'll make 9th power, 3rd power. Okay, so in here, everywhere I'm putting a negative x. Okay, remember, if you have an odd power, the negative stays. If you have an even power, the negative goes away. So this negative is going to stay because it's an odd power. So that's why I'm going to end up with negative 4x to the 5th power. This negative is also going to stay because of the odd power. So I'm going to have a negative times a negative, which is a positive. So I will have positive 3x to the 9th power. This negative is going to stay, odd power. So I have a negative times a negative, that will be a positive. So that will be positive 2x to the 3rd power. This negative is going to stay because there's no power at all. So of course the negative is going to stick around. So plus minus, that's just the same as minus x. So this is f of negative x. Alright, and what we know is if f of negative x matches the original function, then it's even. If f of negative x matches the opposite function, then it is odd. Well, and if it matches neither, then it's neither. Well, what do you see? Yep, f of negative x is a perfect match with the opposite of x. So that means it is odd. Now we should include our little summary statement saying this. So we will say, you know what, I'm going to type it. We will say, since f of negative x matches the opposite function, f of x is odd. Yeah, there you go. Just switch this down. So, it's odd. That's the bottom line. But you got to prove it. If you just say it's odd, that's not enough. It had to be algebraically, and this is how you do it. Okay, again, you always need the opposite function, the original function, and f of negative x. If f of negative x matches the original function, it's even. If it matches the opposite function, then it's odd. This time it was odd. Okay, does the graph represent an even, odd, or neither function? It'll be even if it has y-axis symmetry. Alright, it'll be odd if it has rotational symmetry about the origin. Alright, it'll be neither if it has neither. Okay, let's see what we have. Where is this graph? Can't find it. Oh, there it is. This graph clearly has y-axis symmetry. The y-axis splits this graph right down the middle, so y-axis symmetry, it is even. Okay, where's the answer line? I'll just put a big old even right here for now. Yeah, there you go. The bonus. Find the other two roots using synthetic division. One root is I. We're supposed to find the other two roots. Okay. Well, let's talk about the possible rational roots. Okay, the possible rational roots. Alright, I'll just call them the possibles. Looking at the 5 are going to be plus or minus 1 or 5. You know, the leading coefficient is 1, so, you know, that's automatically the denominator. So, I'm just going to use these possibles and see what's up. Let's see. The other two roots. So, one root is I. So that means we definitely have negative I. Okay, so really we're just looking for one more. Alright, we know that imaginary roots occur in plus or minus pairs called conjugates. So if positive I is a root, negative I is automatically a root. So we just need one more and we're done. So let's start with positive 1. Let's see what happens. So we've got 1, 5, 1, and 5. Wait a minute. Okay, I could do this, but grouping. I see grouping happening. I'm gonna go ahead and do grouping real quick, but then I'll come back and see if this will work also. If you notice grouping, so as soon as I saw the 1, 5, 1, 5 pattern, it just jumped out at me that grouping would be a good option. So I'll come back to, oh, you know what? Never mind. It specifically said using synthetic division, so you know, grouping would work, but we better follow directions. So never mind grouping. Sorry, grouping. Maybe next time. So let's get back to synthetic. Okay, so 1 times 1 is 1. That's 6. 6 times 1 is 6. That's 7. 7 times 1 is 7. That's 12. Okay, that didn't work out. So much for positive 1. How about negative 1? Okay, again, we're looking at 1, 5, 1, 5. Okay, 1 times -1 is -1. That makes 4. 4 times -1 is -4. That makes -3. -3 times -1 is +3. That makes 8. So that didn't work. Okay, we are slowly running out of possible rational zeros. So we did +1, we did -1. Now let's do +5. We've only got these two left, just +5 and -5. So let's check it out. Let's try +5. So again, we've got 1, 5, 1, 5. Alright, 1 times 5 is 5, so that's 10. 10 times 5 is 50, so that's 51. Yeah. 51 times 5, let's see, 51 times 5, that's 255. So what's up, 260? That didn't work. Wow, okay, so we've only got one possible rational zero left, and that's -5. Okie what dokie. So let's just do it one more time. And this better work, that's all I gotta say. Okay, this better be it. So 1 times -5 is -5. That's 0. 0 times -5 is 0. So that's 1. 1 times -5 is -5. So that is 0. Okay, so putting the variables back in, that gives us x squared plus 1. And so that would be a factor, and if we set this equal to 0 and solved it, that will give us the zeros out of it. So if I go ahead and do that, subtracting 1 from both sides, you know what I mean? So I would have x squared equals -1. So this is one of those where you have to take the square root of both sides. So we will take the square root. Don't forget your plus or minus. So that is going to give us x equals plus or minus. Oh, you know what? I was done back here. Plus or minus I. We already knew the plus or minus I. I'm sorry. -5. As soon as we saw that -5 worked, -5 was the other 0 that we needed. We already had the plus or minus I, so I didn't really need to do that last bit. -5, that was the missing 0. So that is it. So the two missing zeros were -I and -5. We knew there would be 3 because of the degree. So one of them was I, and then -I, and then -5. So that was the bonus. By the way, I did this whole test without using the TI-30XS multi-view. If you were allowed to use the TI-30, a so-called bonus problem like the one we're doing now becomes trivial, because we could just put this function in the calculator using the table function. Let's clear that out. So what we have here is x to the 3rd power, use the caret, plus 5x squared plus x plus 5. Alright, so I've just typed the function into my calculator. I like to start off at -10 when I do this. Okay, and so at this point I'm just scrolling down and I'm looking for zeros on the y side. So as I scroll, I see those numbers getting smaller, and then bam, 0 at -5. So right away that tells me that -5 is the other 0. So you know, I could have done that in under a minute and just be done, but it did say use synthetic division, so you really for that reason you needed to go through all of this bees nest. Okay, there it is. That was it for this test. And if you are practicing for something, then you better make sure that you can do every problem on this test without looking. You know what I mean? You make sure you can do it on your own. And then you'll be the bomb. You'll be a beast. Alright, it's been fun. I'll see you on the next video.